Thank you very much, Steve. Can you all hear me, first of all? Is that coming? Okay, great. When Steve asked me to present in this series, this Lubbock lecture series on extremes, I pondered for quite some time about that word, extreme. You know, being an American who's very, very loving of hyperbole, I use the word extreme probably 20 times a day, and now that's 21. And so I thought to myself, well, okay, let's try to tell a story in the session that I have with you, this precious time I have, to try to bring a microscope to what extreme might mean for mechanics. It's not necessarily very obvious what that might mean. Mechanics, of course, is the study of the interaction of forces and the response of a body to those forces. So what could be possibly extreme about that? So what I thought I would do this time is, as I said, I'm going to use a bit of a narrative through some research that we've been doing over the last few years, better half of a decade, I should say, looking at shock cavity interactions as they pertain to solids. I know we've seen bubbles, we've seen a variety of different cavities. This is going to be quite specific in that we're looking at cavities that are present within solid phase material. Right, so, but first of all, let's start with some context. I need to step back a bit because I can't even see my own slides. So it wouldn't have escaped you, of course, that when you look around, we live in a world that's in constant motion. Everywhere around you, everything is busy, moving at a variety of different velocities, and that motion is embodied in a variety of different classes of activities, you could say. So we've got exercise, we've got recreation, we've got professional sports, for example, over here. What else do I have? I've just grabbed things off the internet, of course. I've got transportation, so these can move us around over vast distances very, very quickly. We also have, in some cases, we've got weather. We've got examples of weather producing quite extreme velocities, and that velocities does have correspondingly quite extreme consequences. We've got high-value manufacturing, different variety of approaches to produce components for us to use. And in some cases, we use velocity to study the world around us. Some of you might remember Deep Impact and our direct use at trashing something very, very expensive into seeing what came out of that. And of course, regrettably, we also use velocity, we use motion against each other, unfortunately. Now, if we were to try to put that a little bit more quantitatively, I'm just going to take and tease out a few of those photographs. And so we can plot along the horizontal axis. These are the velocity regimes that we experience on a day-to-day basis, right? So we can have the sort of mundane civilian-type activities in a few miles per hour, but you can see in a professional cyclist probably pushing tens or so miles per hour. We've got some manufacturing processes around the same regime. We move over to the right, we actually have data storage. We've got microelectronic devices which are moving at such rapid speed relative to each other. Here, almost 100 miles an hour, and then not too distant away, we've talked about aerospace, and so we have a jet engine here, and the fan, the tip of that blade as it's racing around that engine could be up to a few hundred meters, miles per hour, 400 meters per second. And as we move along, we've got other examples. We've got Concorde, and we have, even as we go up to very, very high velocities, we have micrometeorite impact onto space structures, satellites and such. So we are accustomed to dealing with systems that are exposed to such a range of velocities. And yet, the world isn't falling apart, at least not in a sort of an engineering sense. I mean, we won't talk about anything else. But if I then use a very coarse term, this is a clumsy term, you're not going to find this term in any textbook. Over-yielding, what is over-yielding? That's just my way of trying to say how much more than the yield stress of the material that you might find in that system would we be subjecting that system to were it to come to an abrupt stop, right? So there's a rapid change in velocity such as, I'm not going to want to point to anything, I don't want to terrify anyone going home and using public transport, but one of these examples coming to rest very quickly would produce stresses that if it was 1, it would be fine, safe. Anything below 1 is okay. There's not a lot on that screen which is below 1. Everything above 1 represents a cause for concern. This is where we have systems which are going to be driven to failure, and that failure could result in quite catastrophic consequences. And we, those that work in impact engineering, our job is to try to understand ways to manage that energy. There's a tremendous amount of energy on this plot, which I've not put numbers to, and if we've done our job well, that means that we can safely mitigate that occurrence where something might abruptly come to a rest, and we could protect the safety of occupants or high-value equipment. that's the context. So how do we actually control impact energy? I mean, this is something that we've seen quite a lot, and actually with the advent and maturation of additive technologies, rapid prototyping, we're seeing that we have exquisite control over the local structure and topology of material systems. So there's a range of materials that we can use to deliberately deform and absorb energy. That's their purpose. Their purpose is to deform. We want them to, otherwise they're going to transfer that energy into us, and that would be a bad day for anyone. And so we've got lots of research looking into how we might sculpt and change the topology and change the structures and orientations of these systems to try to eke out as much energy-absorbing performance as possible. But there's also another possibility, is that because the systems that we use are generally heterogeneous simply meaning I have material in some place and I've got a different material elsewhere, that we could potentially use those heterogeneous structures to focus energy, deliberately tailor where the energy is going and how that energy is released, what time scale that energy is released. And that could be quite interesting because we could use that, as is shown over here, to generate reaction pathways, materials where we want to promote reaction, or in some cases, this is a case I think the question was asked about water droplet erosion or liquid jetting. This is a case where an impulsively driven cavity would produce a jet, and there might be some very, very interesting phenomena that take place were you to place those jets precisely where you want in materials of interest. So what I want to do for the next, I don't know, 20 minutes or so is just to try to answer that first question, is what about impact is actually extreme in here? Okay? And I'm going to tell that through a story, hopefully a quick story, we'll see. So first of all, what do we do in order to do the science to study the response of materials to impact? Well, use this instead? Okay. Shall I start over from the beginning? All right. Is that still okay for everyone in the room? I just shout. Okay, so we do shocking experiments, and that's not a judgment on the quality of the research that we do. They literally are experiments where we are designing a specific impact condition, which is precision impact, and it drives shock waves through materials. And so you could see in this case, this is the type of experiment we would like to perform. We would like to take a spherical cavity. It's an ideal form of a heterogeneity in that it's a sphere. There's material on the outside, there's no material on the inside, and we apply some sort of dynamic loading, which this is what we want to sculpt in the material. We wanted to see a rapid rise in stress, a peak stress that holds for some time, and then we don't worry about what happens after that. And what that will drive is that will drive a shock wave, and what we're interested in is how that energy of that shock wave couples into the cavity and how that energy then triggers certain kinds of responses, which I'll show you in just a moment. So how extreme are these conditions? Well, we're launching things at velocities of anywhere from a few meters per second up to 5 kilometers per second. It's quite a swift speed. So here's a video just showing at the lower end. It's just an impact that we performed. And what I want to call out is this is what the frame rate is. I deliberately put it in seconds so that you can see there's lots of zeros. So there's 12 microseconds per frame. And in one of those frames, our entire experiment's over. Everything else around it's just debris and just a bunch of cleanup. But in terms of the conditions that are produced during this kind of interaction, we produce strain rates of order 10 to the 6. That's a big number. What 10 to the 6 represents, if we were to pull on something at 10 to the 6 strain rate, is it would be a bean sprout that was 30 millimeters high, growing to the size of Mount Everest in the blink of an eye. Blink of an eye is a third of a second. So that's quite a severe amount of strain that we're putting in materials. Okay. And the other thing just to say is that if we want to do this experiment, what we really want to isolate is this initial shock wave as it interacts with the cavity. We would rather that shock wave not bounce around and rattle around and interfere with the very pure type of loading that we're producing. So we've got a massive sample. So what do we do? Well, unfortunately, because it's a large extended volume of material and cavities are by definition inside something, we find it very difficult to peer into the materials, especially if they're opaque. If they're transparent liquids or certain plastics, then yes, we could look inside. But even if you do that, there's some recent work, generally recent work, and what you can see is this is a transparent material. You can see a shock wave driven from the right-hand side to the left. Here's the cavity, and you see very little detail inside that cavity, right? So there's very little that you can really glean from that interaction. So what we exploit then is we use different radiation. We use X-rays, and the particular technique that we use is known as phase contrast imaging. I'm not going to really go into it too much other than to say it turns an image that looks like this,
which is what you could expect to see if you were getting an X-ray at the doctor's. It's an absorption image. It just represents where there's more mass in the way, effectively. And it turns that image into this. And what that does, it allows us to emphasize detail that we couldn't see. Detail that, for all intents and purposes, should not be resolvable. It's smaller than the resolving power or the source size of the X-rays, but we are able and allowing ourselves to amplify through interference, that's all that's showing, where those details are. Okay? So we can play a trick. We can go to very, very high energy, which means that we don't have to worry about absorption. High energy X-rays mean we can put large amounts of materials in the way. And because of the way that the absorption and the phase effects change with energy, what it means is as we go to higher energy, we get stronger phase effects. So there's our technique. Now, the trick is then putting these two together. We've got, on the one hand, what looks like a big gas gun. Well, that's what we call it, actually. It's a gas gun. And we're launching things at many kilometers per second, and somehow we need to do that careful experiments somewhere where they're also doing very careful precision manipulation and measurements using X-rays. And what we need is we need to study cavities where the dynamics are occurring less than 10 microseconds. That's what we showed before, that the entire experiment is over less than 12 microseconds. It's happening so quickly. If we want to excise the information of interest about how that cavity is collapsing, we need to get as much time resolution as possible. We need as many frames of that as possible. So what we do is we go to a synchrotron, and we ask for packets of light. And these packets of light are X-rays. They're very hard, which means that they'll transmit through these materials. And we take advantage of the fact that they can deliver X-rays about every 200 nanoseconds, right? So they're very tightly spaced. So it's quite a few X-rays. And they're so short, so short-lived, that effectively they freeze the dynamics in their path. It's a still shot of that image. Okay? And how bright it is, because we need to make sure that we can detect it using conventional cameras, we need so many photons that the equivalent of running this beamline for 1 second is the same amount of photons that will reach the back of your eye in 9 months. Now, don't try this experiment at home. Leave your eyes, blink as usual, please. But that's how bright it is. There's so many photons in this one discrete packet that we can form a really high resolved image of the dynamics of that system, something that's happening over many, many, many kilometers per second. Okay. So I won't talk about the right-hand side. This is just a scientist's way of saying it was really hard. But it's difficult. We do a lot of stuff. We correct a lot of stuff. And what I'm showing you is the ready-made cake. It's all beautiful. It's decorated. Not what you would see on the day. But in any case, let's have a look at what happens. So here's a shock wave. This is traveling over, so they're 12 microseconds. One frame. Everything that I was interested in is all done. And now I've got to go in and sweep it up. Play it a few times. What you can see, there was a nice circular cavity. There was a shock wave. It raced over to the right. In a few frames, you don't even see it anymore. You can see this racing off to the right. And you see all of this topology of information there that we didn't see before. It's quite fantastic for us. So we can do that experiment a few times. We can run it at a variety of different velocities because, again, we're trying to change the amount of energy we put in. We want to see where the energy is going. And so we can do it at low velocities, medium velocities, and a little bit higher velocities in the strength regime. And I guess the key takeaway is here is maybe you can see evidence of a little shear lip here, and you can see possibly more perturbations. I've put a label there. And as we increase the velocity, the spacing between those perturbations decreases. To understand this, I've just to help you, I've drawn where those shear lips are in this frame here. And we can use a theory of statistical distribution of flaws. We can say in any solid, on any surface, there's going to be a variation in the position of those atoms. There might actually be a macroscopic defect, in fact. But we can have a statistical distribution of flaws. And if they all grow at a different rate, because we're talking about dynamics, the presence of a flaw is to relax the material around it. And so as that flaw grows, you can see a shadow that's growing out, and it's extinguishing these other failure embryos. And those embryos are no longer allowed to grow. And so the final number of fissures that we get, or failure features that we see, is directly a response of the distribution of source sizes. In other words, what is going to fail first, and how hard you hit it, and where the energy is going. Okay? So this is quite important for us because much of this has usually been done by picking something up and looking at it afterwards. But we've been able to do this in real time. So this provides us an exquisite amount of information in order to validate this dynamic shielding theory. We're not really sure what is the nature of damage. As you can see here in one of our earlier papers, we just said cracks. It's cracks. Well, we can go a little bit and we can do what Konstantina has done so well, which is let's try to simulate this in 3 dimensions, right? Let's go ahead and replicate the experiment numerically in a sort of one-to-one, head-to-head simulation. What you can see here, this is that cavity, and I've removed all the material that is not hot. And you can see a projection on the back plane of what the temperature is. And as that moves over to the right, this is moving over in time, you can see that these features that we saw in our X-ray radiographs are actually petals. The petals of damage. And they haven't grown out as a spherical envelope of temperature, but they've actually retained their discreteness, their fineness. And the reason for that is because these are adiabatic shear bands. Adiabatic, by definition, means there's not enough time. We are striking the material so fast, not giving it time to dissipate that energy. That energy remains localized and it sweeps throughout the material, forming this very, very complex and some might even say beautiful crab-shaped topology of damage. If we go to higher velocity, we see that actually we start getting crisscrossing. We get a larger envelope of this thermal mass. And what we can now do is we can correlate the amounts of energy that we put into the system to effectively the volume of heated and activated material. And if it comes to thinking about how we might use it in terms of designing, we could then deliberately place cavities in a certain spatial distribution and exploit the fact that they will all give off heat at a certain time. Okay. This is a rather coarse model. It looks nice, but the details of how we actually controlled or allowed that material to fail within the numerical code is actually really coarse. And so we still don't have any real good information about, at those conditions, the very, very high strain rate conditions, the very high temperature conditions, how that damage and how that plasticity actually evolves. And to do that, we had a very talented group of students who then excise small amounts of material. These aren't necessarily PMMA, but this is a classic experiment where you would take very thin slices of material, and instead of using a gas gun, we want to look at the very first instances of relaxation, very first instances of compression. And so we make the material as thin as possible. We strike it on one side with a laser, and being very careful, we make sure that we test the material in a regime where you'll get an elastic response and a plastic response. So it's analogous to what we would do in a lab when we're doing quasi-static loading, where we're looking for the yield point. So we're just looking for a dynamic yield point. And we could also then, with a probe beam, measure on the rear surface and say, okay, well, then what should pop out should be an imprint of elastic behavior followed by plastic behavior. And as we have done before, we look for that folding over, or in this case, it's this kink in the curve, and that represents the yield stress of the material. Now, what it might surprise you is that I'm increasing the temperature in this. This is aluminium. And as I increase the temperature, conventional wisdom would say it should get softer. But it gets harder. It doesn't just get harder. It gets harder by orders of magnitude. So that's really surprising. So we had some thoughts, and we had a very talented then student, now associate professor over at Birmingham, who put together one of the first fully elastodynamic models for dislocation dynamics. Dislocations, of course, they are the defects, they're the agents of plasticity. And all you need to really know about this equation here, which represents sort of the plasticity that can form in a material, is that it's mediated by 2 factors: motion of dislocations and also generation of dislocations. And so what he was able to show is that under those conditions of extremely high strain rate, dislocations, the effect of a dislocation appearing, popping into a material, moving around, isn't felt throughout the body instantaneously. It takes time. It takes time, which is associated with the characteristic sound speed of that material. So here you can see an actual wave front of a dislocation that's moving, and this wave front wouldn't be felt by the shock front until it had communicated forward enough. And the relaxation that we actually see in the shock front is due to the superposition. Basically, all of these wave fronts, as they arrive at the shock front, they will mediate that stress, and we'll finally be able to measure the dynamic yield strength of the material. And what we found is by increasing temperature, it actually takes longer for those waves to get there, so this is why it was relaxed less. And so there's this counterintuitive interplay between temperature as well as strain rate. And we can even go further. I promise 2 more slides. We can even go a little bit further. We can say, okay, well, we've looked at what happens over 100 microns of material, but let's look at the very first instance of compression. So that's after 10 picoseconds. Let's dry this material. Let's look at strain rates, which are so high that I can't think of the number of zeros after it. And let's see if in this equation, where before it was essentially governed by the first term, motion, what happens if it's governed by the second term? And Benyat, this talented student, he performed a simulation where he threw away all the dislocation. He said, let's pretend it's pure. And what he was able to do is he was able to replicate and match the experimental data that we've got, principally the yield points here, by allowing an eruption. You can't see it here, but this is 1 times 10 to the 16 dislocations, from 0 to 10 to the 16 dislocations in a period of time of around 10 picoseconds. Right? So that's quite an astounding response that we weren't expecting, is that homogeneous nucleation all of a sudden takes over when you start to apply loading at ever faster rates. So, my final slide, I promise. To answer the question I asked myself and you all at the beginning, what is extreme then? In terms of mechanics, what does extreme mean? And my definition then of extreme is whenever we load a material faster than the material has time to communicate the information that it has even experienced a load to the rest of the body. And when that happens, you start to frustrate the natural mechanisms for relaxation, and new activation, new energy pathways for dissipating that energy must be exposed. So we see this play out in this, a variety of different length scales. I think, as in the interest of time, I won't belabor them, but effectively at the large length scale, we saw that an initial shear crack would extinguish adjacent shear cracks. We saw that when dislocations move, their effect isn't felt until some time later, and that will relax the front. And we see that if we go to even higher strain rates, then in fact, we can drive the system to produce its own dislocations because there's not enough dislocations there in the body to accommodate that strain. Okay. And how we're using it, I know I put this in a very specific box about cavities, but there's many other mechanisms that I haven't even discussed that we are cataloging carefully for each material, and we use this in a physics box in order to design materials and understand how those materials will absorb energy. And but the very sheer fact that shock compression activates all mechanisms at once and allows them to naturally compete, that allows us to get this very exquisite detail and the natural response of materials at high rate. So, thank you. I know that was a bit blistery, but hopefully that was okay.
Thank you so much, Dan. Questions? Gentlemen here.
I have a sort of comment, and maybe the previous presenters might want to comment on this as well. Have you ever looked at cavitation? I mean, you know, because they say that when the liquid droplets actually, when the bubbles collapse in the liquid, a very high pressure waves are produced.
I can say yes. So I didn't show it because I was more interested in this in the strength. I thought that would be good for this audience. But we've also, when we impact these cavities at above 2.5 kilometers per second, they fluidize. Right? And what we do is they're an impulsively driven collapse, where you saw in one of the previous slides. I guess just as a token to the fact that we have done this before. Here. Here, there you go. You can see this fluid jet, right? And that can happen naturally, certainly when it's near a surface, and there is, of course, interest in trying to look at the interaction of that cavity with a surface for maybe the reasons that you're alluding to for shock peening or the sorts of surface preparation techniques.
Any comments from Constantino or Chiara?
We have looked in modeling this numerically, but when you're using CFD, it's hard to model the effect that it has on the surface. We can model the jet, we can model the change of pressure, but we haven't coupled it on the fly with what happens to the material. We can take the pressures as an input and implement as an output and implement as an input to a different type of software that can account for mechanical changes to the material, and I think that's a really nice work. And we have done the droplets that I kind of skipped, which was very interesting to see, up to 500 meters hitting a surface and trying to visualize inside.
I mean, I was going to ask you a question about that as well, because I thought I was going to say, could you use an experimental measurement to actually observe these collapses in the bubble formation and those sorts of things in real time? And hopefully the answer is yes.
I'm glad to hear, actually.
Good.
It's great. Sounds like all three of our speakers are going to have a research project together.
Thank you. Very impressive work. I just wondered, in a practical sense, what links this would seem to have relevance to some of the mechanisms that First Light Fusion are using to try and generate fusion. I just wondered if you had an interaction with them and how this work is informing their development.
Yes, actually, very well spotted. So we have been working with First Light. In fact, this project on cavities was sponsored by First Light. They're a very good collaborator in that they generally said, we'd love you to investigate diagnostic techniques to look into the interior of objects. And then we took that in a very general, liberal sense. We've now been awarded with them Prosperity Partnership that's led by Imperial College and also involves York and also Oxford Physics, which is dedicated to trying to address three key challenges that First Light have identified related to hydrodynamics, heat transport, and radiation transport. So my role in that will be in trying to now look at things that are a little bit more interesting from their perspective. Yeah.
Any other questions? Microphone coming from the other side.
Hello, Douglas Craig, 1983. I was wondering, is there any crossover between your work, your lab, and the material science department? Is there collaborative work going on in this field?
I guess my pause gives you an answer. There's not interaction, but this lab is in Begbroke, and so there's less traffic that would take place if we were on the main site. We do have proposals in together with the materials engineering group here at Oxford for big centers that are currently in the work. So if that does come off well, then yes, we will be working with them for the next 5 years at least, yes.
Okay, thank you.
Yeah. And we have time for, I'm going to be very selfish and ask a question. Oh, there's somebody up at the top.
Okay. Yes. So there are different ways in which you can take a perfect material or material that has defects and produce an increased number of defects, so these dislocations. One is through heterogeneous nucleation. That's, for example, classical Frank-Reed sources. These would be pre-existing defects that then in a certain way that they evolve, they would then emit new dislocations. And so that has a lower energy barrier. It doesn't take quite as much energy to get them to activate. Homogeneous nucleation takes advantage of the fact that you just, in any pure solid, you still have a statistical misarrangement of those atoms. And so if the threshold is high enough, you can actually produce a defect where there was nothing before. So that's what that is. That is a higher energy pathway for producing damage within a material. And it really requires those extremely high strain rates in order to do that.
So my question, Dan, if I may, is you are very elegantly quantifying if for want of a better phrase, a series of coordinates which describe physical characteristics associated with materials under high stress, under extremes. Once you have that and your computational models, it seems to me that you can do the equivalent of drug discovery in the sense you can give constraints, design constraints, and hallucinate and find novel materials which potentially are outside of the ken of existing materials science, maybe using something like high throughput AI. Is that something that excites you or horrifies you?
Well, I'm very much excited by the vocabulary just to use that. That sounds like it just writes itself, but absolutely. That's the other side of the work I wouldn't have been able to show. What we do with this information is then we put all of the physics into, compared to what you're doing, very basic optimization, materials optimization routines, and allows us to anneal the microstructures to try to exploit or try to optimize a certain defined target. But I imagine, and because it's not my area, I imagine there's probably a lot more that we could do. So absolutely, I would love to find a way to get some of that information to you.
Fantastic. Dan, thank you so much for a great talk.